Henri.
Thank
And
you.
final talk of the session will be by Jason Jackiewicz from New Mexico State University, who will be telling us about stellar astrophysics, binary systems using the ARC 3.5 meter telescope. All right, Jason, go ahead.
All right, thank you, Eric. The captioning is pure poetry. And I'm going to put you on a different page, Eric, so I can ignore all the warnings. And hello, everyone. I'm Jason Jackiewicz at NMSU. I'm going to talk about some work with at least the people mentioned here, postdocs and students over the past 7 or 8 years using the ARSIS spectrograph, looking into binary systems. And this work has touched on, at least more than we thought it would, various topics that you see on this slide, and I don't have time to discuss all these. I'm going to focus on just one of them, and it is the first one, astroseismic scaling relations. So our idea a long time ago, when Kepler observations were being provided to the community, and we were learning a lot about pulsating stars that we had never really thought possible. Our idea was to look at ways to test some of the theories of seismology and some of the results that it was giving us, and what better benchmark systems than eclipsing binaries, of which Kepler had detected thousands, at least since its entire mission. And so the idea, again, I'm just going to focus on this one aspect. The idea is, here's a power spectrum of a Kepler red giant. And so you take the light curve, and if you look at its frequency content, you see these nice peaks that are due to resonant standing acoustic modes in the star. And there are two pretty straightforward, relatively straightforward quantities that one can measure. By the way, these are red giants, which pulsate at a much lower frequency than, say, the sun, at least this particular one, in order of magnitude or more lower frequency. But you see labeled on this figure two quantities, this delta nu, which is a separation of frequencies of the same angular degree in different radial order. Anyway, it's this comb-like pattern that you can measure, and this other one called nu max, which is basically where the power spectrum, if you could fit a Gaussian to this, where that power peaks. And those two quantities, turns out from theoretical aspects, delta nu is related to the density of the star, and nu max can be related to the surface gravity. But you can combine various relations to derive a pretty, again, straightforward way to calculate masses and radii using those two quantities, and the effective temperature, which you can get relatively easily from other observations. And so at the time, and in the early Kepler years, in the 2010, 11, these relationships were being applied to thousands and thousands of pulsating red giants that were observed by Kepler to get the masses and radii, test theories of stellar evolution across the galaxy. There are over 20,000 pulsating red giants observed by Kepler. And this idea of ensemble astroseismology, by applying equations that even I can solve for, what was very was the thing to do. And these relations, as you see, though, are scaled to the solar values of these quantities, and that can seem problematic. Because we don't even actually know these two quantities extremely well for the sun. We know its temperature, I think, but there's still debate about what these quantities are for the sun. So if you don't have these reference values right, you can affect the mass and radius, obviously. And two, we're applying these we're applying these relationships to stars that are at a much different evolution state. For example, red giants than the sun. And so there's many reasons to want to make sure that these actually work the way they're expected. And an idea was to estimate these parameters in an independent way using eclipsing binaries. And we found a large sample of red giants that were also part of eclipsing binary systems. These are power spectra from Kepler data of a sample of them. Over the years, we've observed over 100 targets at APO and at various epochs of their binarity. And this is just some subsample that I grabbed. So here's the idea. Again, you have, say, a red giant system and a main sequence star, either a hot or a cool star in an eclipsing system. This figure illustrates the two eclipses that are very common for these, where the red giant eclipses the main sequence star and you get a flat bottom eclipse. These are actual binned Kepler data folded on the phase of the binary. And typically in the case where the other star passes in front of the red giant, because of limb darkening, etc., you get these rounded bottom eclipses. And so from the orbital mechanics of this, you can derive properties of the stars. And in particular, if these stars are double-line spectroscopic binaries, of which a fair number have been, you can get mass and radius in an independent way from seismology by solving for computing the radial velocities. And so just to summarize a bit of that, we have, say, a red giant star and a main sequence star, and these are various quantities one would want to know about both of them. These are various ways of getting, say, mass and radius using orbits and independently astroseismology. When you throw in spectroscopy, you get a third way of deriving surface gravity and get other quantities of interest for models like metallicity, etc. And so this spectroscopic aspect here, and implicitly in the RV section here, is really what led us to get to try to get a lot of observations at APO of these systems. One fun system, I'll just go through it to show you what happens, was an eclipsing binary with two red giants, a double line spectroscopic binary. And when you take a spectrum of these, you can, or when you take many spectra, you can disentangle the radial velocity of each component, and this is called a broadening function. Some of you may be familiar with it, but at every epoch, you see these two peaks, which are derived from the spectra, which denote the radial velocity of each component. And once you obtain the radial velocity of each component, down here, you see the radial velocity of the red and the pinkish points through the orbital phase. We had a lot of observations of this one particular system. And I read the requirement that you had to show APO data for your presentation. And in this figure in the black is a spectrum of this system. And using the radial velocities, you can disentangle the spectra to get two individual spectra of the two red giants, hopefully. And from these, say, you can measure the metallicities of each component. Hopefully you get the same answer, or or anything else you'd like to. For this particular system, it was interesting because only one of the red giants was oscillating. And so we only had an astroseismic measurement of one of the two, and we're not exactly sure why the other red giant, it's rare for red giants not to have detectable oscillations, why it wasn't. But nonetheless, we were able to model this particular system. This is kind of an HR diagram, given the masses that we derived from the orbital solution. It turned out we can only find models that for the masses we derived, we could only find a solution where both stars barely had the same age if these were horizontal branch giants and not on the RGB. So these are core helium burning stars. It was a challenging system, even though on the surface it looks pretty straightforward. But this is showing that if you draw a horizontal line here, you barely get through the model location of these stars as they're coeval, whereas on the RGB they are not coeval. Again, it's a tentative conclusion, but anyway, so we took a lot of spectroscopy for many of these systems. This is showing all our points along an orbital phase for another handful of stars. So lots of nights at APO, and these are fairly faintish systems that we need a longer exposure time to get good radial velocities, around a half hour or so on average. So it's a slow process. I'm going to skip this and get to the punchline, which was we were able to initially, and since we've done more, but we were able to measure the seismic masses and the orbital dynamical masses, we call them, of 9 red giant eclipsing binary systems shown here. And what you see for these 9 Kepler stars are the masses, the dynamical masses as the black star with error bars, and the other points are various astroseismic scaling relations applied to the power spectra of those stars. And hopefully you can see that seismology seems on average to overestimate the masses. If we consider the dynamical masses ground truth, overestimate the masses by about 15% and the radii by about 5%, even when these scaling relations use different types of corrections and empirical corrections and things. So that's an important result that we found, and this figure just shows when you overestimate the mass of red giants, at least, and all stars, that you underestimate the age by various amounts. For the low mass stars, it could be by 10 gigayears, which is a lot. These are some of the systems where if we apply our errors to, or the mass overestimation, we see how much we underestimate the age. So it has consequences for how we understand the galaxy, given the large population of red giants in it. And finally, over the years, we've collected a big sample of the ones that are ideal, the oscillating red giants and eclipsing double-line spectroscopic binary. We've found 13 out of the 14 known in the Kepler catalog and analyzed them. Overall, we have a big sample, about 16 now. It's small numbers, but it's been useful, and we're looking into other possible systems that we can study too. And I won't talk about the ones that aren't oscillating. I'll save that for another talk. So I'll just leave up my some papers if you're interested in this work, and stop there. Thank you.
All right, thank you, Jason. As usual, you can ask your questions on the Zoom, in the Slack, or raise your hand. And in the, I see a hand raised from William.
Hi, Jason. Just a quick question. Have you checked if any of the stars in your sample have interferometric radii measured?
Yeah, so that's a good point. There has been other tests of seismology by trying to measure direct radii using interferometry. You're right. Most of those that have been done and published have been on main sequence and subgiant stars, not necessarily more evolved red giants. There are a couple, and within the error bars, typically the radii tend to be a bit better estimated using seismology, and then that as well. So the radii from interferometric results, and as you get closer to the main sequence, it's even better, seem pretty solid.
Thank you.
Okay, and last 30 seconds, Enrique.
Hi, Jason. Thank you. So I'd like to know what is the lowest metallicity of the stars you analyze? And also, I'd like to know if have you compared this to new isochrone feeding techniques like those from Star Horse and from isochrone, and if you can comment on that.
The lowest metal, we haven't had too many really low metallicity stars. These are mostly, you know, disk giants, so maybe 1.5, -1.5. And I have some other slides on that on a different thing. So nothing too extreme. And then, yes, in a recent paper, this top one actually, we've compared with isochrones, some of the other properties we've derived, and we still see some issues with new isochrones, very new isochrones. So I would point to this top paper actually.
Okay, thank you.
Thank you.
Okay, and that wraps it up for the STAR session. Nancy, do you want to make any announcements, or should we just jump straight into break?
I think we can just jump straight into break. We'll reconvene at 15 minutes past the hour to start the AGN session. So thanks everyone for a great first session. Look forward to seeing most of you back here in a few minutes.